Sometimes you like to roll your sleeves up, other times you don't, you know? The duality of woman. All right. After a devastating mass extinction wiped out 85% of species alive on the planet, life was starting to recover in ways the world had never seen before. It was the start of the Silurian period, which lasted from 443 to 419 million years ago. During this time, vertebrates started to get major upgrades, new traits that are still around and crucial for survival today. And invertebrates started to migrate to seemingly inhospitable habitats. Plants and fungi had some cool new shit going on, and of course during this time there were specimens that were weird as fuck. I'm gonna put this all into a little rundown and give you a glimpse of what life was like during this global metamorphosis. My name is Lindsay Nikole, and this is the history of life on Earth, that we know of. Alright, let's get the global conditions out of the way. Supercontinent Gondwana, as you would probably guess, is still hovering over the southern pole. There's a chain of some smaller continents kind of hovering over the equator. If you remember during the Ordovician mass extinction, the world was smacked with a global cooling. Glaciers sucked up some sea level, which led shallow water habitats to not exist anymore. But then the Earth looped back around with a backhanded global warming. So going into the Silurian, those glaciers melted, which led to much higher sea levels, and land masses got covered in shallow seas. This made for a nice and cozy expanse for marine inhabitants, and allowed many groups to recover. If you remember during the Cambrian and Ordovician, the fishes were pretty much tadpole-like in shape, jawless, sucking shit off the ocean floor, and that's all there was to it. So what were the fishies up to now? Well, this is the time they went absolutely berserk. Diversification off the charts. Jaws appeared for the first time. Different types of fins, ray fins, lobe fins, cartilaginous skeletons, jawed fish with armor. Characteristics that were the building blocks of lineages that would allow them to interact with the world in unbelievable ways, such as me, using my finger to point to my mouth to tell you about the evolution of jaws and lobed fins. Holy fuck. It's like evolutionception. Let's start off with what probably perked your ears up in that list, the development of jaws. This is a weird development because it seems like something that appeared out of nothing, even though obviously it didn't. Recently, for some reason, I've been getting more DMs than usual asking about the mechanisms, the process of evolution. You know, like, I get that whales evolved from land animals, but what? Huh? And I just finished reading The Selfish Gene by Richard Dawkins, so I'm feeling real fresh, and I kind of want to over-explain the development of jaws to use it as an example in this case to help like visualize it. Also, read Selfish Gene if you haven't already. I was probably assigned that in biology class and just didn't read it, and so I just finished reading it for the first time. It's great for understanding this. It's long, so get the audiobook, listen to it like a podcast. Boom. Easy. Okay, so like I said, jaws didn't appear out of nowhere. The classic idea is that they evolved as a modified form of a trait that was already existing in jawless fishes. They're gill arches. Gill arches are structural loops made out of bone or cartilage that support the structure of gills in fish. They've been present in vertebrates since the Cambrian, so have essentially been a component of fish since the beginning of fish that we know of. Gill arches are great for increasing the surface area of the gills, which allows more oxygen to get into their body at a given time. Absorbing oxygen more efficiently is obviously beneficial to the survival of the little guy. So gill arches that are more and more efficient are going to develop over many generations, as variation in that trait in the population will give some an advantage over others. Little guys with slightly more efficient gill arches are likely to survive and pass on those genes at a slightly higher rate than others, and so on. So these gill arches became more modified as time went on, and something strange happened. The pair of gill arches closest to the mouth pushed forward over time for efficiency until they were essentially around the mouth opening, creating some sort of basic form of a mouth structure. Now, these gill arches, which had a primary purpose of getting oxygen into the body more efficiently, served a secondary purpose, providing a very basic and very slight form of grabbing power, giving them a slight advantage over the ones still stuck sucking up shit from the ocean floor with no structure. This provided a blueprint for those modified gill arches to evolve over time, for more efficient grabbing power as generations went by. This developed into a stronger and stronger structure until it could eventually be labeled as a proper jaw by our definition. And of course, remember, these changes happened at an unnoticeably slow rate. Like, you can't expect to watch grass grow if you sit there for a bit, but if you come back a few days later, you gotta mow it. There have been some changes. But like in this case, come back after millions of years, thousands of generations, then you can mow it then. I mentioned this as the classic idea because as technology has advanced, there are new hypotheses developing based on like gene expression and shit. But I'm gonna stick to the classic idea because it's still valid. As of right now, it is still accepted and it is simple and a good example. And hopefully it was a helpful example. And if not, I will eventually try again at a later date. Actually, you might remember that I talked about it before with the brittle stars that can see without eyes in the all-stars video. Their chromatophore network likely assisted in camouflage and predator avoidance, and just so happened to make an impact on their existing photoreceptor network that allowed them to sense light versus no light. When those two networks kind of pushed into each other, it somehow created some sort of an image, allowing them to see without eyes. The technical term for this is an exaptation, a trait that takes on a function different than its original function. So, back to this particular exaptation, the development of the jaw. It obviously helped fish go bananas. New niches and strategies developed for this cool new weaponry. So, allow me to introduce you to these first jawed fish that appeared in the Silurian, the placoderms. The Silurian was their bread and butter. They developed armor for protection, pectoral fins for balance and stability, and primitive tail fins. And look at that, we still see fins today. And they diversified to shit. Actually, let's draw a little cladogram, a little map, so we can keep track of all this. The development of jaws led to placoderms, and placoderms diversified to shit. So jaws led to placoderms, and placoderms are the ancestors to bony and cartilaginous fish. Yes, from the shark video. Chondrichthyes, the cartilaginous fish we know today as sharks, skates, and rays. These are the roots of that lineage. The acanthodians, also known as spiny sharks due to their shark-like appearance, even though they were not sharks. Just at the base of the lineage that would eventually lead to sharks. They first appeared here during the Silurian and existed for like 200 million years, and were found in oceans all around the world, so very successful group. Spiny sharks only had teeth on their lower jaw, and some even seemed to have replaceable teeth at this time. They had big eyes and were likely active predators, feeding on crustaceans and other fish. Okay, so that was the beginning of the cartilaginous root. On the bony root, there were some notable species. Bony root, bony skeletons, like Intelinathus primordial, whose name essentially means complete primitive jaw. The first fossils of them were discovered in China back in 2013. Matter of fact, take a shot every time I say China, because it's gonna come up a lot in the next like 2 to 4 minutes. They're seen as a transitional species between more primitive and modern fish due to their particular set of characteristics. Another one from China, called Chilinu rostrata. Kind of looks like a dolphin. Really exemplifies the fact that shit got weird almost immediately after jaws evolved. The bony fish went in a couple directions as well. The ray-finned route, with fins made of cartilaginous rays. This is most fish alive today. Think goldfish, think blobfish, think my son the deep sea telescope fish, think betta fish, etc. There was also the lobe-finned route, with fins made of a series of bones. Think coelacanths, think lungfish, think us. Yeah, these were the ancestors to tetrapods, animals with 4 limbs that would come a bit later, like Tiktaalik, amphibians, dinosaurs, the platypus, etc. These bony fins eventually led to the evolution of the limbs we know and love today, but we'll get to that in a couple episodes. But let's get back to the net. One of the earliest lobe-finned fish that we know of is called Cerolepis ramiri. Another one first found in China in 1998. They had some pretty gnarly teeth for their time. And the largest Silurian lobe-finned fish that we know of is called Megamastix, which means big mouth blunt teeth. They're pretty much considered the first vertebrate apex predator that we know of, and could get to like 3 feet long, 3 times the length of any other fish alive at the time that we know of. They were also found in, you guessed it, and kind of changed the way science viewed Silurian fishes, because before their discovery in 2014, fishes were thought to be pretty restricted in their size at this time. At this point, I'm sure you are downright exhausted hearing me talk about fish, and I am absolutely exhausted talking about it as well. Let's move on to the spooky shit. Erase. All right, the strange specimens. Starting off with a group we are already familiar with, the sea scorpions. Yeah, they were somehow still kicking after the Ordovician mass extinction and hadn't even hit their prime yet. These apex predators continued to be apex predators pre and post-extinction, and even beyond the Silurian. Their most heinous form during this time was Pterogodus, one of the largest sea scorpions to ever exist, that we know of. They could get to about 6 feet long, with fossils found on every continent except Asia and Antarctica, at least for now. Fossil evidence suggests they had a pretty advanced visual system, all the better to see with, as well as extremely strong punching and crushing chelicera, all the better to punch and crush with.
Anyway, I started blasting, bang!
Suggesting they were, not surprisingly, a high-level active predator. A horrifying trailer for the forms that were to come in the millions and millions of years later, that we will get to in the next period. And what about the trilobites? Yeah, they somehow also survived the land plant apocalypse. They did lose about half of their diversity, which was obviously not great for them, but they did recover pretty quickly and still managed to inhabit every corner of the earth, except for the poles. So yeah, trilobites were still around, still doing their little block and roll pose. Here's one that is definitely unlike anything we've talked about so far. Solacina Cthulhu, a more recent discovery from the UK in 2019, and named after the Lovecraftian tentacled monster. They had 45 tentacle-like feet they used to crawl along the ocean floor. As you have probably guessed, based on the fact they were found so recently, we don't know much about them. Scientists figured out they were some sort of early echinoderm related to sea stars, sea urchins, sea cucumbers, etc. All the weird animals I talked about in the All-Stars edition of What the Fuck Is This? But what particular echinoderm form form were they most closely related to? Let's take some guesses. If you had to guess, do you think Solacina Cthulhu would be most closely related to sea stars, brittle stars, sea urchins, or sea cucumbers? Take a good second to think about it.
A lot of fresh gas! Fuck! Gas! Gas, goddamn you! Why won't you answer me?
The answer is sea cucumbers, which might be the most surprising based on appearance. So let me explain how scientists figured this out. They used a 3D reconstruction process called high-resolution physical optical tomography, a name you have absolutely no reason to remember. What they do for this 3D process is grind down the fossil layer by layer and take a picture at each layer, like fucking claymation, you know, like moving it a little bit, taking a picture. So you're left with hundreds of photographs that can be kind of stacked on top of each other to create a 3D shape. It's like 3D printing, but completely opposite. This 3D model of Solacina Cthulhu helps scientists look at their water vascular system, a body system that echinoderms use for fucking everything. Locomotion, food and waste transportation, respiration, an all-in-one system. Like the men's 10-in-1 shampoo that you can use for like toothpaste and also motor oil. Solacina's particular water vascular system had sea cucumber-like traits. So that is the understanding for now. Other than that, what else can you say about a creature that looks like this? Just classic case of a little guy that hangs out. Another strange specimen from the Silurian was a nyctozoon, an animal that, like hallucigenia from the Cambrian, was so bizarre scientists initially had it flipped upside down. It was first discovered in Scotland in the late 1800s, but wasn't described, i.e. given a scientific name, until almost 50 years later. Nobody wanted to touch this thing. Couldn't even give it a best guess. The first jab at classifying it, and the scientist who named it, was DJ Scorefield in 1937. He understood it as some sort of proto-chordate. You remember chordates, like us and all other vertebrates and tunicates, are a little phylum. Protochordates are earlier offshoots that kind of split off before chordates became true chordates. So chordates and protochordates have the same characteristics generally, but they go about them in practice differently. They develop differently. Honestly, it doesn't even matter for this conversation because Scorefield was wrong. We know that now. But this wasn't known for a long time. So for the next 60 years, a nyctozoon was studied even more based on the assumption that they were a protochordate. This was unbelievably confusing, like trying to figure them out with a starting point of wrong. You know when you have those really long math equations where none of your steps are making sense and you're doing extra steps that aren't even remotely close to what you learned in the lesson plan, then you go back and you realized the first answer you got in the first step was wrong? That was the study of this creature. Then finally, in the 90s, new, more well-preserved fossils were found and helped scientists realize that they had their shit all mixed up. The previous fossils were all smushed up and laterally flattened. The reconstructions were all turned around and shit. These new fossils were now three-dimensionally preserved. Soft tissues were preserved, and their traits, now in clear view, lines them up very neatly with arthropods, specifically thylakocephalans, an extinct group of crustaceans alive from the Silurian, maybe Ordovician, to the Cretaceous. Finally, it was making sense. A nyctozoon and its relatives had bulbous compound eyes and raptorial limbs. Absolutely precious little guys. All right, I now want to introduce you to my favorite Silurian strange specimen, Aquilonifer spinosus. That doesn't sound right. Aquilonifer spinosus. What is going on here? It was found more recently in 2016 in the UK, and this is the reconstruction we're now working with. Definitely some sort of arthropod, right? With appendages coming off of each segment, kind of like centipede or millipede-like in form. Real thick antennae that kind of look like they each have individual sentience. And then weird bulbs attached to long threads attached to their back. Are those parasites? Is this some sort of unusual plant-animal combo? A symbiosis of some sort? No. Those little tether balls have been determined to be babies. And the main guy those bulbs are attached to is the mama, or papa. This is an individual with its 10 juvenile offspring attached to it by long strings. A parenting style unlike any we're familiar with in the natural world, but that we can definitely draw parallels to in the classic American mall. The parents with kids on leash backpacks. Kids can have fun and not stray too far from their parents, find themselves in any danger. Parents can go about their business without the weight of a child on their back. Of course, there's always a chance that I or any other passerby will trip over the kid, but that's not my problem. That's on them. Aquilonifer spinosus was named after their resemblance to kites. Their name means kite bearer. I like it a lot, to be honest. I feel like I can imagine what it would be like to crawl along the ocean floor with creatures attached to you by string. I'm imagining it right now, and it feels really natural. I feel like I've done it before. I think I was maybe this in my past life, and I honestly don't mind it. All right, we're moving on to the next section of the video. I'd mentioned in the introduction that a major event that happened in this period was the invertebrate migration to seemingly inhospitable habitats. The habitat in question was land. While we humans enjoy a crisp autumn morning or a summer breeze in July, the transition to land might as well have been hell on Earth, and a journey our own ancestors, the vertebrates, wouldn't be ready for another like 50 million years. Some arthropods, though, just felt like they saw what they needed to see in water, been there, done that, and were ready for a new challenge. One that had dry, suffocating air, gravity on full blast, desiccation around every corner. But it was a habitat of opportunity as well. Plants to feast on with no competition, no predators lurking in the shadows. Very promising. These arthropod pioneers had a long road ahead of them. Lineages had to go through small changes that built up over millions and millions of years to allow them to live on land full time. Their exoskeletons evolved to be waxy and waterproof to prevent desiccation and evaporation. New respiratory structures emerged, etc. One of the first full-time residents, at least that we know of, is called Pneumodesmus pneumoni, a millipede-like myriapod. So millipede relative, but not millipede. I talked about them in one of my first YouTube videos, millipedes, so I'm just gonna give them a quick little rundown. If you wanna learn more about them, go to the video. Pneumodesmus pneumoni was a pretty typical millipede, even though it wasn't. But this fossil had openings all over its exoskeleton called spiracles, which proved to be a very crucial find for the invertebrate transition to land. Spiracles are tiny networks of tubes that allow air to diffuse into the bodies of arthropods, specifically myriapods and insects, a working terrestrial respiratory system. These networks would end up playing a huge role in the evolution of arthropods, especially, most notably, in the Carboniferous period, which we'll get to in a couple episodes. While Pneumodesmus pneumoni is the earliest terrestrial arthropod we can put a name to, there's trace fossils that have been found even earlier than them, possibly even going back into the Ordovician, which I mentioned in the last video. These are tiny little footprints, some of which have been found in the largest organisms on land at the time, the giant fungus called Prototaxites. It could get to 26 feet tall and 3 feet wide. And no, I will not be hearing anybody out. Prototaxites was first discovered in the mid-1800s and was later described as some sort of giant rotten conifer trunk. We now, of course, understand that trees didn't exist yet, that we know of, but this was the 1800s. They had very few puzzle pieces to work with. Later attempts to classify them included giant marine algae, lichens, or even rolled up mats of liverworts. It was a pretty gnarly debate for like 160 years, until just the last couple decades where now a general consensus has been reached for team fungus. Scientists have been able to detect specific carbon isotopes in the fossils that point to fungus rather than plant. So, giant fungus. Exactly what this fungus looked like is more of the debate now. At one point, I think scientists were playing around with the idea that they could have looked like giant mushrooms, cute little head, which would have been sick. But I think gravity and the lack of fossil evidence removes that possibility, unfortunately. The most common reconstruction is this skyscraper look, which is definitely what they would have looked like to the only animals on land at the time, the little millipedes. The orientation is based on their similarity to tree trunks, but new evidence suggests that they were just as likely to grow horizontally as they were vertically. And of course, the network they had underground must have been fucking nuts for how big they got. So they were probably growing, who knows, fuck which way all over the place. The Silurian was a big time for plants too, evolving systems that would eventually allow them to grow so big we could drive a fucking car through them. So I think the best person to explain this monumental time for plants is the plant expert, Joey, from Crime Pays But Botany Doesn't. He must know, like, every single plant dude, and he's a total badass. Luckily, I was able to track him down while he was on the road to put a little clip together for this video. If you don't know him already, you're gonna fucking love him. So, here he is talking about prehistoric plants.
So today we're going to talk about the Silurian period and the plant life that existed on Earth's surface at that time. And there wasn't a lot. At least there's not a lot that we know of. Only a few dozen genera. But first we got to talk about what Earth's atmosphere and landscape were like at this period. Now keep in mind there wasn't much soil yet. Okay, to get soil you need weathered rock and organic material. The weathered rock part is easy. There's plenty of rocks exposed at Earth's surface, of course, at this time. But the organic material part is a little bit trickier, okay? It's thought that most of the organic material, if there was any, came from decomposing lichens. Now, of course, the lichen's just a symbiosis between an ascomycete fungus, generally speaking, and an algae. The fungus kind of farms the algae, if you want to think of it like that, but there's no plant life involved. But they can weather and break down rock, and then, of course, when the lichens die, that eventually would build soil. That's an organic material to actually build soil with. But regardless, there probably wasn't a lot of soil, and it wasn't very nutrient-rich or very deep. Certainly, those plants had their work cut out for them. Oxygen levels were certainly a lot lower at this point too. Today they're at 21%. In the Silurian period, they were roughly around 14 to 15%. CO2 levels back then were also 10 to 15 times higher. This would have been a very uninviting place for any vertebrate alive today, right? It'd be choking, suffocating, and extremely warm. That said, this is when plants are thought to have really gotten going. The first plants stayed kind of close to the freshwater, little inland estuarine systems that they are thought to have evolved out of. None of these got very tall, okay? These kind of formed dense, probably what looked like a taller shag carpeting of green around the margins of some of these freshwater ponds. Now, the two most famous genera are the genus Cooksonia and the genus Baragwanathia, both of which had vascular systems, which is pretty impressive. They had internal plumbing. So these were vascular land plants, Cooksonia and Baragwanathia. Cooksonia looked kind of like a whisk fern today, just a leafless green photosynthetic stem with little cups bearing sporangia at the distal ends. It probably topped out at 6 to 8 inches, in some cases maybe 12 inches tall, and Baragwanathia looked like a big green pipe cleaner, kind of more akin to today's lycopods, like Lycopodium, Lycopodiella, etc. But either way, these were not astoundingly complex photosynthetic life forms. I mean, for the time they were, but compared to what we think of today, these were not that complex. Caia was another genus. C-A-I-A was a non-vascular plant from this time period. Zosterophyllum is another one that actually had, I think, Zosterophyllum had a vascular system, but either way, it was just one of these, green pipe cleaner looking things. But think of all the plants that we'll never know existed because they never got fossilized, or the rocks that they were fossilized in later got destroyed. I mean, it can be kind of a trick to find rocks that are from that actual age of Earth history. Totally different time period. I mean, it would look so foreign to anything that we know of today. And that's kind of what has me so fascinated with it. I mean, just to imagine what those ecosystems look like, and also to imagine what was evolving and what the selective pressures and the environmental stresses that these things had to deal with back then. I mean, especially CO2 levels and heat. And then just the lack of soils too. I wonder what humidity was like too. That would be a weird thing. Moving from water to land and having to deal with the threat of drying out, the threat of desiccation. That's a whole other palette of environmental stresses and selective pressures that can direct your evolution. So either way, totally different time period to think about. Might as well be another goddamn universe, but fascinating nonetheless. And again, we've only got a small glimpse of what was actually going on back then. It's like trying to put together a 1,000-piece puzzle when you've only got 9 or 10 of the pieces. So anyway, that's all I got for you today. Have a good rest of your day. Go fuck yourself. Bye.
A phenomenal sign-off. That actually really sums up how the Silurian period ended. Periods that end with some sort of extinction have a pretty clear-cut boundary on where one period ends and one begins. Kind of visualize it in the rock. The most extreme case being the KT boundary, with the asteroid going all over the place. The iridium in the asteroid that wiped out the dinosaurs can be seen all over the world. The Silurian didn't have this. Kind of just ended. Kind of a go fuck yourself to scientists, because they had to get a boundary internationally recognized by a committee of specialists, which didn't happen until 1977. They marked the end of the Silurian and the beginning of the Devonian by the first appearance of a graptolite species called Monograptus uniformis. Graptolites are colonial animals, and this particular graptolite species first appeared about 419 million years ago, in association with some trilobite and conodont species. Whatever. It's just complicated, and that's the point. But there were some minor extinctions that happened throughout the Silurian, specifically 3, that played over a time span of like 10,000 to 200,000 years. The first one was a global cooling event that also had a huge drop in deep ocean oxygen about 434 million years ago, leading to the extinction of many deep ocean and open ocean species like conodonts, trilobites, and graptolites. 6 million years later, there was another minor extinction, another oxygen drop that led to the extinction of 95% of graptolite species. Tough shit for them. And the last one, 4 million years later, seems to have been due to a global sea level drop due to glacier formations that wiped out a shit ton of graptolites and some additional conodonts. These extinctions likely played more of a local role than a global one, but were extinctions nonetheless. By the end of the Silurian, the Earth was ramping up to introduce the largest predators the Earth had ever seen that we know of. So stay tuned for that in the Devonian period. All right, moving on to today's questions. What do you think is the most prolific homosexual in the animal kingdom? Lots of animals get homosexual on occasion. Unsurprisingly, lots of mammals. Even more unsurprisingly, I'm going to say the most prolific homosexual, other than humans, are our closest living relatives, the bonobos. Bonobos get down with the get down, especially females. It's like well documented they scissor more than they breathe. So I'm going to say that. Next, help. This giant bug is just living on my patio. It looks like a moth with tiny wings. It's maybe 1.5 inches to 2 inches long. I live in Southwest Florida. That is some sort of a hawk moth, which are found in many different regions, especially in the tropics. So that checks out for Southwest Florida. Hawk moths are generally 2 to 8 inches long and have some pretty cool looking caterpillars called hornworms. Hawk moths have the longest tongues out of moths and butterflies that we know of. They're long as fuck, and they're pretty much harmless other than the occasional damage to crops. do to their babies. If you have a weird animal identified or a question you want answered, let me know in the comments, and I might feature it in the next video. So be sure to subscribe so you don't miss it, and to continue watching how the history of life on Earth unfolded that we know of. A massive thanks to Joey for coming on to talk about the development of plants. Be sure to check out his channel that I'm going to link in the description. Check out my Patreon for our Discord server and live streams. And for now, stay curious. The world has a lot for us to learn. See ya!